Hello, my name is Leslie Coro from Math 4411, Abstract Algebra. Today we're going to be going over rings and Hensel's lifting theorem concepts. Rings comes from abstract algebra, while Hensel's lifting theorem comes from number theory. I've worked out both of these in a way. Rings from this semester, abstract algebra, and for number theory, Hensel's lifting theorem was my project that I decided to go over and break down. Basically, with this project and video, I am looking into seeing how these two can correlate together. One from abstract algebra, the other from number theory. So I'm hoping to be able to make an understanding from both of these in this presentation. The introduction I want to start with is that the study of abstract algebra uses algebraic structures that has rings and groups in them. Rings are actually very useful in different mathematical concepts, including in number theory. So that's where I got my idea to be able to use it for Hensel's lifting theorem, which was my number theory project that I did, and found that both of these could work together. So basically our goal would be connecting the two concepts from abstract algebra and number theory together and see what we find out from it. What exactly are rings? That's the first question that we're going to be having. Rings are basically a set of two binary operations of either addition or multiplication. There are different ways to satisfy by abelian groups, multiplication, and using distributive law. Some examples that I found that I could use for rings would be the use of integers, rational numbers, polynomial rings, and also the modular arithmetic, which my example right there is a small little one. Now we'll be looking into the special types of rings, such as PID, which is also known as principal ideal domain. Usually generates one single element, so it could be such as integers. For local rings, is usually the unique maximal, which is very helpful from what I found out for number theory and different number theory concepts. So an example could be the integer of p is equal to a over b that belongs to a rational number where b is not equivalent to 0 mod p. For the complete ring, usually it respects of the matrices, so such as the integer of p. Well, p-adic integers. Now we're going to be breaking down Hensel's lifting theorem. We have a better example later on in our presentation, but for now we have f of a is equivalent to 0 mod p, while f prime of a is not equivalent to 0 mod p. It's basically what we are given at the start, so being able to build it up together. So we have f of a and f of prime of a. So we look at those two and then we work them out. Afterwards, our solution would look more into the second bullet point, which is f of x doesn't belong to 0 mod of p to the power of k, where x is equivalent to a mod p, which that would be our solution, basically what we were looking for. Now we are looking at how we can connect the two. First bullet point basically is that the p-adic integer, which is basically a type of number that is part of a general set in all, is categorized as a complete local ring. So to continue on, the converge of a lift that has to be completeness. So there has to be completeness for it to be lifted. So that basically could give us that portion of the p-adic integer. And due to p is classified in these maximal, so p we're going to go basically on where with the Hensel's lifting theorem we saw earlier, it's let's say 0 mod p. So that p portion would give us that idea. And then the structure of the ring, we use derivatives from mod p. So it could be inverse. There could be other forms that can happen, but the more classified and more clear would be having a form of inverse. Now we'll be looking at an example of the use of Hensel's lifting theorem. This one is in a non-uniqueness problem. So basically I grabbed this from my number theory project and I wanted to just use it mainly because I feel like this one was good enough to show how Hensel's lifting worked. It wasn't too difficult, nor was it too easy where it was enough leveling. So we started off with our x to the power of 2 plus 2x plus 1 is equivalent to 0 mod to 2 to the power of 3. So 2 to the power of 3 shows the lifting part. So that's not too bad. Afterwards, we go ahead and bring it down, and we get x is equivalent to 1 mod 2. From there, we're able to convert to the left side, where we see there f prime of x equals to 2x plus 2. We continue it by doing f prime times 1, so then that would equal 2 times 1 plus 2, which gives us 4, which is equal to 0 mod 2. Since 0 would be, there would be no remaining on that portion. Afterwards, we get x equals 1 that continues to f is equivalent to 0 mod 2 squared. Right here, we see that we're able to get multiple solutions. So I went ahead and brought it down and went for x is equivalent to 1 plus 2t mod 4. Then we have our two separate sections. X is equivalent to 1 mod 4 and x is equivalent to 3 mod 4. We continue on with x is equivalent to 3, which is equivalent to 3 to the power of 2 plus 2 times 3 plus 1. We basically get that from the beginning problem, so we break it down from it. And that becomes equivalent to 16. It would be equivalent to 0 mod 8. And basically, again, 0, there would be no remainders on that. The lifting part would be x is equivalent to 3 plus 4t mod 8, while our values would be x is equivalent to 3 and 7 mod 8. In conclusion to this presentation, to be able to summarize everything back up, the p-adic integer is essential in Hensel's lifting theorem. That's what we found out in general for this presentation. The reason why is how the structure is needed to be able to lift the solution from mod p. To be able to go for a higher power. So where we find out that mod p can continue to mod p squared and mod p to the cubed and etc. It can continue on forever. We also found that Hensel's lifting theorem is powerful in abstract algebra, as it helps different forms of equation to be able to make things simpler solution by lifting it. To be able to be more of a complex number system. And that's basically how I understood that for both of these concepts, even though in different areas of mathematics, are still able to help each other out and be able to build each other of a form of clear understanding on both areas, such as, honestly, with Hensel's lifting theorem, it could be slightly confusing to understand why there's a lifting power to it. And honestly, if we look at what we're given with the p-adic integers of rings, we could see why and how it could be understood by both of those concepts. And for my final slide, here are my references. I went ahead and saw 2 YouTube videos that basically gave me an outline over Hensel's lifting theorem, a quick refresher. The other one also gave me a bit of an understanding over rings. And then the textbook that was for abstract algebra that was able to give me a better understanding of what I'm solving for and what I'm looking for this presentation. Thank you for watching, and I hope you have a great day.